the comparison between different naming strategies and data consistency models through system design, prototype simulation, and performance analysis. Now, I'll be walking you through our distributed system design. Our goal was to build a functional prototype of a key value store that simulates the real-world challenges of a distributed environment all within a single Java virtual machine. We adopted a modular client-server architecture. Each component, whether it's a client, the storage node, or the naming service, is implemented as an independent Java thread. To ensure we are truly simulating a distributed system, these threads never call each other's methods directly. Instead, they communicate exclusively through message passing. We use link blocking queue to simulate the network interface card for each node. To find these nodes, we implemented a centralized naming service. It decouples logical names like storage primary from physical node IDs. We compare two structures: flat naming, which is a fast hash map lookup, and structure naming, which mimics DNS by traversing a hierarchy and adding latency for each level. The heart of the project is how we handle consistency across replicas. We use version value objects to track the freshness of data. In our sequential consistency mode, the primary node logs until every follower acknowledges a replication request. This guarantees no stale reads but makes writes slow. In eventual consistency mode, the primary returns a success message immediately and replicates in the background. This is much faster, but as our metrics show, it introduces the risk of stale reads. Finally, to test our system resilience, we built a network router. This isn't just a pass-through. It introduces random delays and can even be configured to drop packets to simulate network partitions. This allows us to observe exactly how the system behaves when a replica falls behind or the network becomes unreliable. By collecting metrics on operation latency and stale read rates, we can clearly see the trade-offs between performance and consistency in a distributed landscape.
Overall, the system simulates a distributed storage system with naming service. The main component includes simulation threads representing distributed processes, naming service for logical network resolution, and storage nodes for data writing and replication. Two architectures are executed concurrently to allow direct performance comparison. The first architecture uses flat naming with eventual consistency where data is replicated asynchronously to multiple replicas. The second architecture uses structured naming with sequential consistency where write operations are confirmed synchronously. Each architecture runs in its own thread, simulating a parallel execution in a distributed system.
Now let's look into file and package. The first one is the main simulation file. The main entry point of the system is the main simulation file. This file is responsible for starting the simulation and launching multiple simulation threads. It creates two simulation threads, each representing a different architecture, and starts them concurrently. The second one is simulation package. The simulation package contains the simulation thread class. This class extends the thread class and defines how each architecture behaves. Inside this file, the run method controls the simulation flow, including starting timestamps, executing naming resolution, performing write operations, and measuring latency and throughput. The third one is naming package. The naming package contains the naming service. The flat naming service simulates a flat name resolution mechanism, while the structured naming service simulates hierarchical name resolution. Each naming service measures resolution latency using high-resolution timestamps. And the last one is storage package. The storage package contains the storage nodes class. This class simulates data storage behavior under different consistency models. Sequential consistency confirms write synchronously, while eventual consistency propagates data asynchronously to replica nodes using background threads.
The console output provides a detailed view of how the simulation behaves. The timestamp at the beginning of the output indicates when each simulation thread starts. Simulate timestamps show that the simulations are running concurrently. Naming resolution times are displayed in nanoseconds, allowing precise performance measurement. For eventual consistency, the output shows propagation delays to multiple replicas, demonstrating asynchronous replication. At the end of the simulation, total latency, throughput, and the number of replicas used are displayed for each architecture.
Hi, my name is Ramana Morgan, and I will analyze the performance metrics for the flat eventual model of our system. The flat eventual model runs 5 operations. The average naming time from the system is 1.10654 milliseconds, which then gives us a total naming latency of 5.5327 milliseconds. From the system, it is also found that the total operation latency is 6.6363 milliseconds. Thus, by subtraction, it is found that the put latency is 1.1038 milliseconds. Keep in mind that the initial resolution time for each operation is higher due to dominant overhead. Now, considering the naming latencies, the average get latency is 1.1065 milliseconds. However, this isn't the steady state of the system due to the dominant overhead. The steady state is calculated by excluding the first operation's resolution time, which gives us an average get latency of 0.00525 milliseconds. Now, by comparison, it is found that the flat eventual model is heavily read-optimized, as it requires approximately 42 get operations for a single put operation. This shows that the system architecture is designed to handle higher volumes of read operations. The throughput for the system is relatively high at 569.7 operations per second because this model uses asynchronous replication. Now, under no failure, the model's throughput decreases, put latency minimally increases, and get latency has a high variability. The put latency's increase is because the main thread does not wait for the data to travel to a neighboring node. The decrease in throughput is due to connection hangs, whereas the high variability of the get latency is due to the fact that the system waits for a TCP timeout when the data is unknowingly stored in a failed node.
In this section, I will briefly compare the structure sequential model and the flat eventual model based on the 3 performance metrics: total latency, naming resolution time, and throughput. First, in terms of total latency, the structure sequential model record a latency of approximately 16.17 million nanoseconds, while the flat eventual model achieves a much lower latency, about 6.64 million nanoseconds. This significant reduction occurs because the flat eventual model uses multiple replicas and allows parallel processing, whereas the structure sequential model processes requests sequentially using a single replica. Next, for naming resolution time, both models show very similar performance, with an average of around 1.1 million nanoseconds. This indicates that the naming mechanism introduces minimal overhead and does not significantly impact our system performance in either model. Finally, regarding throughput, the structure sequential model achieves approximately 271 operations per second, while the flat eventual model more than doubled this value with about 570 operations per second. The higher throughput in the flat eventual model is a direct result of concurrent execution and replication. In conclusion, while both models perform similarly in naming resolution, the flat eventual model clearly outperforms the structure sequential model in terms of lower latency and higher throughput, making it more suitable for scalable distributed system. That's all for
To wrap up our simulation, demonstrate the classic trade-off in distributed system. The flat eventual model is clearly rate optimized and designing for high throughput, making it ideal for systems like social media where speed prioritized over immediate consistency. However, for environment where data accuracy is non-negotiable, the structured sequential model is the better choice, as its blocking synchronization ensure a strict global order and prevent state break. By understanding this naming and consistency model, we can design more resilient and efficient distributed architecture. Thank you.